We present GoVMP Global Optimization for View Motion Planning in Fruit Mapping. Crop monitoring optimizes yields and detects anomalies, but manual monitoring is labor-intensive. Robotic automation enhances efficiency and scalability, especially in large-scale glasshouses. Autonomous crop monitoring faces challenges such as fruits being outside the camera's field of view and occlusions from complex plant structures. The image illustrates these issues. Where blue highlights occlusions by leaves and magenta indicates fruits needing further exploration. We previously developed a view motion planner to address occlusions and enable exploration while minimizing motion costs. This planner was deployed on our platform in a real-world glasshouse environment. The external view of the system is shown on the left, while the arm camera's perspective is displayed in the top right. The planner constructs a view motion graph and identifies the currently predicted best path, shown as cyan lines. Using this approach, we are able to detect partially observed fruits and discover new ones. Specifically, this view motion graph is constructed by sampling views and associated motion costs, shown in gray. However, this VMP planner's greedy search selects a sequence of views and connecting paths, shown in cyan, without guaranteeing full coverage. To address this limitation, we introduce a globally optimized view motion planning strategy. We begin by identifying informative look-at voxels that are likely to contain fruits in their surrounding regions. Similar to VMP, we consider three types of look-at voxel boundaries. These boundaries help in detecting hidden fruits occluded by plant structures, discovering additional plants, and completing fruit surface observations. We further consider a fourth type to incorporate region priors. It refers to the unknown voxels within an inflated octree, in which the regions of interest, namely the fruits, are expanded by a fixed distance, shown in blue, thereby providing prior knowledge for subsequent global optimization. Next, a view pose is defined by a 3D position and an orientation. We sample a set of view poses whose orientations are directed toward the identified look-at voxels. For each randomly sampled 3D position within the workspace, we perform occlusion checking and use inverse kinematics to verify the existence of a collision-free joint configuration. The arrows indicate the camera's viewing direction toward the corresponding look-at voxel associated with each sampled view. Finally, we perform global optimization on the constructed graph. It integrates two key components: a set covering problem to guarantee complete coverage of all informative targets, and a shortest Hamiltonian path problem to minimize robot motion costs. On the left, the figure shows yellow targets that must be fully covered by selected views capable of observing them. We prioritize coverage of existing fruit regions by using ROI unknown and region prior look-at voxels as our targets. On the right, the view motion graph depicts the selected green views and their purple connecting paths, achieving full coverage with the shortest motion paths, ensuring both efficiency and effectiveness in monitoring. Starting from a random viewpoint, we demonstrate our system using a robotic arm equipped with an RGBD sensor on its end effector. After the initial mapping, the system performs global optimization and generates a sequence of views and connecting paths, shown in cyan. The robot follows the collision-free motions along these view paths to explore the scene, detect additional fruits, and also improve coverage of detected fruits. The map is updated when a new view arrives. Due to the newly acquired information, a new graph is created and the view paths are re-optimized. The robot traverses the new paths again to further enhance fruit coverage. To mimic the large-scale real glasshouse environment, we set up the simulation in Gazebo and conducted quantitative comparison with baseline methods. Here, we showcase a clip of the complete fruit mapping mission. Because the robotic arm's workspace is limited, we divide the environment into multiple segments and use a trolley to move and elevate the arm between them. The robot operates each segment until the specified time limit is reached, then moves on to the next segment. As shown in the table, the quantitative results demonstrate that our GEO VMP achieves a superior balance between fruit mapping performance and robot motion cost. Compared to the motion-efficient VMP, Go VMP achieves significantly better mapping accuracy with only a moderate increase in motion cost. Compared to the coverage-focused NBVSC, it substantially reduces motion cost while achieving slightly improved mapping performance. In summary, we propose a globally optimized view motion planning framework that integrates set cover problem and shortest Hamiltonian path problem to replace the traditional greedy search. This ensures complete coverage of informative targets while following a globally shortest path, enabling our GEO VMP planner to effectively minimize motion costs while maximizing fruit coverage for efficient autonomous fruit monitoring. We validate our approach through real-world demonstrations and simulated glasshouse experiments, providing quantitative comparisons against baseline methods. Thanks for your attention.